Okay, this video will represent the last of the new material for this particular lesson. Week number 2, lesson number 4. Let's talk about significant digits. This is something that you may or may not remember from high school. I don't even know if you went over it in high school. It's the kind of thing that my particular degree is in math and physics, and we really did not use very much in math at all, but we did use it a lot in physics labs. So significant digits is an important part of what you learn if you are also paralleling a science career. If not, then you should know what it is. I do not know if they ask about this on Praxis or not, but we want to make sure that we're at least aware of significant digits. It's not particularly complicated, but it's the kind of thing you got to do every now and then to just keep yourself brushed up on, okay? Example, you weigh yourself on an inexpensive bathroom scale that can only measure your weight to the nearest tenth of a pound. You weigh 132.3. So to say your weight was 132.300 pounds would be misleading, because this implies that the scale could make measurements that go to the nearest thousandth, and it doesn't. So significant digits has to do with accuracy. A non-zero digit is always significant, and we'll give you some examples of these, but this might be a good thing to get a picture of to put in that album on your cell phones. Zeros that follow a non-zero digit and lie to the right of the decimal point are always significant, okay? Zeros between the non-zero digits, as in 4002 or 3.06, that's always significant. So you count the zeros if they're included in between numbers. They're just like any other digit. Zeros to the left of the first non-zero digit, like 0.006, 0.00052, or if you really wanted to get extravagant, 0.0001531. Zeros to the left are never significant. And zeros to the right of the last non-zero digit, but before the decimal point, are not significant unless stated otherwise. So 40,000 or 210. In the case of 40,000, there would be one significant digit. In the case of 210, there would be two significant digits. All right, so let's take those ideas and let's start applying them. Here's the rules for counting significant digits again, okay? All non-zero digits and any zeros contained between the non-zero digits count. So look at the number. It's in green there, 300042. There are 6 significant digits there. You include the zeros because they're bookended between regular digits. Leading zeros do not count. So 0.000034, only 2 significant digits. Trailing zeros count if there is a decimal point. So if it says 0.0002500, there are 4 significant digits. Notice the first 3 being leading zeros do not count, the ones in black, but the 2 green ones do count because there is a decimal point. Next, trailing zeros may or may not count if there's no decimal point. So we want to go with the most conservative answer. 190,000, is that what that is? Yep. Then you have 2 significant digits, the 1 and the 9. All those zeros afterwards are not considered significant digits. So state the number of significant digits and the implied precision of the following numbers. Let's try the first one, A. Now you'll notice if I underline that, okay, zeros after the decimal, okay, zeros after the decimal are considered significant digits. So I underlined all of them, seeing that they're all significant, and that gives me a total of 6 significant digits. What about letter B? What would we get there? In that one, remember, leading zeros do not matter, so only the 9 and the 8 are significant, so you have 2 significant digits. What about the next one? Zeros between the 4 and the 1, zeros that are contained and covered by, if you will, the left and right regular numbers, digits, then they're included. So that's 4. What about next? Now, this one you might think of this as a little tricky, but the decimal point 0 is what makes this really important. These are trailing zeros, but they do count at this point because of that decimal point. So I have 4 significant digits there. Next up. Yep, those zeros are contained between the 1 and the 98, so they are significant digits. They're all included. Next up. Okay, the 202 is a significant. Leading zeros are not significant, so there's only 3 particular significant digits on that place. Okay, so again, this is a good strategy to underline it and then to follow those rules that are there. Maybe you want to take this particular slide and take a picture of it, put it in your album so that you can follow along. I would also expect one of these on your upcoming quiz as well. Okay, understanding errors. Look, there's a couple of ways to do math. You've had enough classes with me to know that I'm pretty good at random errors. I seem that they're totally unpredictable, and I have made them my entire life, and I don't think I am going to stop making them. The good news is I do really, really well with concepts. I understand concepts really well. I am not so good on the details. Sometimes I just make the dumbest mistakes, random errors. Systematic errors are different than random errors. Okay, while random errors are unpredictable, systematic errors, they refute, or also called systemic errors, they occur because there's a problem in the measurement system. And it's going to affect every measurement the same way. I'll give you 2 examples. The first one is the protractor on the left. Now, if you look carefully, the 180 to 0, it doesn't make a straight line. So therefore, every degree measurement is going to, well, not every, but many of the degree measurements are going to be off a little bit. 90 degrees might be right. I remember one year we had to give our kids these big new Common Core state tests, and the state, what a ripoff, boy. The state actually forced you to purchase protractors from a particular company. You talk about a political kickback. We had to buy from this company, which we did, our district did. And then when we got the protractors, they were like cockeyed, and they didn't even make a perfect 180 degrees. And every single angle measurement that the kids took was off. So they couldn't even do it correctly. So the systemic error, or the systematic error, was that the protractor was messed up. It wasn't that the kids couldn't do it, and the questions weren't, the mistakes weren't random, like I make random mistakes. These mistakes were made because the protractors were screwed up. Or look at this particular ruler. Like a lot of kids will just put the end of the ruler, and that's where they'll start measuring. But if you notice, the measurements don't start at the end. So because of that, you'll see students get this wrong as well. Okay. In the following, describe any likely sources of random errors and any likely sources of systematic errors. An average income of 25 people found by asking them their incomes during interviews conducted at a supermarket. Okay, so what are some random errors and what are some systematic errors? Okay, so for some random errors, well, first you're only asking 25 people, so you're not likely to get a particularly good statistic. Okay, and then there's luck. Which 25 people do you get, right? It's kind of random in who you're choosing. And the other thing is, do the people even know their income, like completely off the top of my head? Like there were times when I knew around what my income was, but I didn't know exactly what it was, and I was surprised to find out afterwards. What are some systematic errors? Well, what time of day are you going? And I don't mean this to sound insultory in any way, shape, or form, but if you go to a presidential election, this is a general statement. This is not an absolute statement. Are we clear on this? But generally speaking, older people who are retired, they tend to vote earlier in the day, and people who do not have a job tend to vote earlier in the day. Each of those subsets of people tend to vote a particular way, Democrat or Republican. However, the polls might say such and such a candidate's in the lead, but there's a systematic or systemic error in those polls, because then when all the people who get off of work, who tend to vote a particular way in certain areas, not all areas, will come in, and they will greatly shift the results of that. So The time of day that you're asking. You know, you're at the supermarket and you're asking people. There's a lot of people who are at work at that particular time of day, and there's a chance that they make more money. What day of the week is it? You know, if you're asking on the weekend, then less chance of a greater chance of the person working during the week. Which supermarket? In upstate New York, there are two supermarkets that are pretty popular in terms of people like to make trips there. I forget the names of them because where we live in Callicoon, there's one local grocer, and it's not a full-size grocer. Only 800 people in Callicoon. One is Hannigan's, or Hannaford's. And the other one, I don't remember the name of it, but I think it starts with a B. And they're really nice. They're really, really nice. And you're going to pay a little bit of extra there. And, when my wife and I were first married and the kids were young, I used to coupon clip and store everything and only go on sales. And I would shop at any food place, as long as it was a clean food place, to buy what I needed for my family. But as time went on, I began to appreciate going to a supermarket where maybe they had a little bit more homemade prepared foods and so on, and you pay more for that. So people with more money are likely to go to a supermarket like that. And also there's time of year. I worked at a grocer on Fire Island. I was a butcher there for a while, and if you went before Memorial Day or after Labor Day, it was the local crowd. In between, it was all very, very, very wealthy New York City people. So that would also affect the results of any polls or questions that you may make. Okay, next up, absolute error versus relative error. An example of this, and this you will have a good amount of this on your test coming up, so be prepared for it. The actual distance to Paradise, Pennsylvania is 13.34 miles, but your odometer reads 13 miles. Okay, what's the absolute error? Well, the absolute error is always the measured error minus the true value. So, if the measured error is 13.0 miles and you subtract the 13.34 actual miles, you come up with negative 0.34 miles. Now, the relative error is going to be that distance, but then you have to divide by the actual mileage, the true mileage. So you have to divide that by 13.34 and of course convert it to a percent, and that would become negative 2.5%. Okay, so absolute error is the actual difference. Okay, and then and when you do that, you're going to take your reading and then subtract the actual difference. Okay, that's your absolute error. Then you have to divide by what the actual distance is to find your percentage. Okay, find the absolute and relative errors. Go ahead. So in this particular case, the absolute error is the measured minus the true, which is 30 minus 29, which is going to equal 1. And then the relative error is the absolute divided by the true, which is 1/29 times 100% to convert to a percent, and I get 3.4%. So that's relative error and absolute error. Remember, absolute error is never a percent. It's just the actual amount, okay? And then to convert to relative, you always want to convert to a percent, which means you're going to have to divide and then move the decimal 2 places to the right, which is what multiplying by 100% does. And it's always going to be the absolute over either the original or the true or whatever's the real value. Okay, accuracy versus